Hi, everyone. Thank you guys for joining us. We're just going to wait a couple more minutes to allow some more people to log on. Thank you for joining us. We have a great program for you guys, so thanks for your patience. All right, I think we're going to get started, everyone. Thank you guys for joining us for this month's Full Steam Ahead webcast. We have an awesome program lined up for you guys with some of the best and brightest students and young professionals working in the geothermal field. Right now, we're going to share some of their award-winning research. They are scholarship recipients from this year's scholarship program. But first, would love to thank our Earth Energy Visionary members, BHE Renewables, Ever, Exceed Geoenergy, and SLB. We're very grateful for their generous support of Geothermal Rising and therefore the Full Steam Ahead webcast series. Also, of course, our Geothermal Champion members. You can see them all here. There's a lot of them, so I won't read them all out to you, but grateful for their support as well. So this is not the right, there we go. So we're just going to start with a quick introduction. That's going to be from our own Vanessa Robertson, who will give you a little bit of an overview for the scholarship program. And then we'll go into the main event, the excellent presentations from the 3 scholarship winners that we have represented here. And Vanessa will give you all an intro to them and their bios, but kind of the structure will be they'll each give a 10-minute presentation of their research, and then we'll have 5 minutes for Q&A. So please drop your questions in the chat during their presentations, and then I'll read them out to them for them to answer during those 5-minute Q&A sessions. So I will pass it over to Vanessa.
Wonderful. Thank you, Anina. And thank you everyone for logging in today. Super excited to be here to welcome these incredible students that I've gotten to know virtually over the last year or so. So a little bit about the scholarship program. So the annual Geothermal Rising Marcelo Lippmann Scholarship, named in honor of a former board member who managed the Lawrence Berkeley National Laboratory's geothermal program from 1985 to 2000, celebrates the outstanding contributions of students in the geothermal field. Over the course of his career, Marcelo Lippmann authored more than 100 technical papers and reports, leaving a lasting impact on the geothermal community. This year, we awarded $3,000 each to 6 graduate students, providing support to advance their research or ease the financial burdens many students face. We were thrilled to receive nearly 30 applications from 19 schools spanning 9 disciplines and 10 countries, our highest number of applications ever. This record-breaking response is a testament to the growing global interest in geothermal energy. If you would like to support the scholarship, donations are greatly appreciated and tax deductible. A donation link will be shared in the chat. But enough from me. Let's hear from the students themselves. First, I'm excited to introduce Margariete Malenda. Malenda received her bachelor's in geology at Kutztown University of Pennsylvania and received a master's in geochemistry from Colorado School of Mines. She completed her PhD in geophysics at Stanford University this past August, where she explored the impact of rapid temperature decreases on the transport and elastic properties of geothermal reservoir rocks. Welcome, Margariete.
Great, thank you all. I'm wondering if you see what I see, which is the slides themselves and not my notes.
Yes.
We're all set? Okay, great. Yeah, as Vanessa said, my name is Margariete Malenda, and I'm very honored to be here and to share my research with you all. Just a couple of notes. If we run out of time for questions, or like you still have questions, my email is here and I put slide numbers at the bottom of the pages. So we'll hop into it. Today is basically just a very small snippet of my PhD thesis. And I've basically studied how to stimulate geothermal reservoirs from an experimental perspective. So when I say geothermal reservoirs, you might think of your conventional geothermal systems that are more shallow in the subsurface. And we call them conventional because they have naturally high permeability. They're made of rocks like the sandstone here with lots of pore spaces. That's not what we're going to talk about today. Today, we're going to focus on what we call enhanced geothermal systems that are much deeper in the earth, and we're interested in them because they tend to have a lot more heat than many of those conventional systems. But there's a really big challenge with these enhanced geothermal systems. Because they're so deep, we're dealing with basement rocks. And because we're dealing with basement rocks, those rocks don't have a lot of permeability. They're what we call tight lithologies. And rather than looking like that sandstone I showed you before, they have microstructures that look like this, where we have mineral grains that are very tightly mated together. So we don't have those nice big pore spaces that I showed you in the last slide. So this poses a challenge. We have low permeabilities. There's no pore spaces to flow fluid through here. If we're going to have any pore space in these tight lithologies, they're going to exist in microcracks. So microcracks are really tricky to deal with because they have very small pore volumes. They're very thin features, so they're very pressure sensitive. And this is basically where my thesis has been focused on, is how can we increase flow through features like these cracks? Well, this basically calls for a stimulation method, right? So you can think hydraulic fracturing, hydraulic shearing. My thesis focused on a stimulation method called thermal shock stimulation, where rather than relying on increasing pore pressure to make channels for fluid flow, we rely on temperature changes in the reservoir. So I can describe how it works in a couple of simple steps. We have our geothermal reservoir here and a plant, an injection production well. The first step is we create a thermal gradient by injecting surface water. So that water is cooler relative to the reservoir. That temperature change causes thermal stresses of the mineral crystals. Those minerals respond by either expanding or contracting, creating thermal cracks, and these cracks form channels for fluid flow. Now, steps 1 through 5 are what we're going to call a single thermal shock cycle. But in reality, when this is done, there are repeated thermal shock cycles. So you would pause injection to allow the reservoir to heat up again, and then you might repeat injection over and over. So it's cyclic thermal shock stimulation. Now, you can imagine with this practice that it's very intensive. It uses a lot of resources like water, we could say. So my thesis has been focused on how can we optimize the stimulation? How can we get the most bang for our buck, you could say? How can we get the greatest permeability increases for a number of thermal shock cycles? Now, anytime you want to optimize a process to get a desired result, you have to figure out what controls how that process affects that desired result, right? So for my thesis, I looked at what is the impact of lithology-specific microstructures on controlling the thermal cracking and the resultant permeability increases of those rocks. So I'm really interested at what happens at the microscopic scale and how it impacts these bulk properties like flow through the rocks. So I was interested in different types of different types of rocks that exist in geothermal reservoirs. So I did a literature review to look at what sort of rocks comprise geothermal reservoirs throughout the world. Turns out there's a lot of felsic rocks, a lot of carbonate rocks, and a lot of mafic rocks. So this led me to choosing 3 lithologies for my thesis: Sierra White granodiorite, Mount St. Angelo carbonate, and Mount Etna basalt. So 3 different rocks. All of my samples have very low porosities. And they all come in these samples like this that are little cylindrical plugs, 1 inch long, 1 inch diameter. And despite the fact that all of these rock types have low porosities, they all have very unique microstructures, as you can see here. The granodiorite's got tightly mated minerals. This carbonate, even though it has low porosity, we have these vuggy pores. The basalt has pre-existing cracks in it. So all same flavor of tight lithology, but all very different microstructures. Now, it's not just the physical pore spaces and grains that could affect how a rock responds to thermal shocking. It could also be the thermal composition of that rock, right? So each rock has a different thermal composition, and that's dictated by the thermal properties of the minerals that make that rock up. So I found out what sort of minerals comprised my samples, and I found that in the granodiorite, there's a lot of plagioclase and quite a bit of quartz. The carbonate is almost all calcite, and the basalt has a lot of plagioclase. We can then look at the thermal properties of the minerals. So for the granodiorite, we can look at properties like volumetric expansion. So basically how much a mineral expands for a given heat input, and also thermal conductivity, which is the ease of heat flow through that mineral. So basically, the further we are in this corner, the easier it is for a mineral to conduct heat, the more it's going to expand, the more you might expect a response with a temperature change and thermal cracking. So we see in the granodiorite a lot of heterogeneity in the thermal properties of its minerals. For the carbonate, we have relatively lower thermal properties of this calcite, so we might expect less cracking. And same thing for the basalt. We have relatively lower thermal expansion and conductivity, so I might expect less thermal cracking as a hypothesis. So we've met the samples that I worked with. Now let's segue into how I thermally shock them in the laboratory. I can explain this to you in 3 pretty simple steps with this temperature versus time plot. The first step is I very, very slowly heat my samples to a given reservoir temperature, which in my case was 350 Celsius. And I do so by just putting them in an oven. I let the sample sit in that oven for a period of time, and then I take the samples out of the oven and I quickly put them in a bucket of water. It's pretty simple. And this is how we simulate 1 thermal shock cycle. When I wanted to test the number of thermal shock cycles, I basically just repeated steps 1 through 3 over and over and over. And this is what this looks like in the laboratory. We have the oven, the sample, the bucket of water. It's pretty straightforward. So we've seen the samples, we've seen what I do to test thermal shocking on the samples. So now let's take a look at the impact of this repeated thermal shocking. This is the results for the granodiorite after 0, 1, 3, and 10 thermal shock cycles. So what I've observed is a lot of crack elongation, primarily along the boundaries of different mineral grains, which is pretty interesting. And what's even more interesting is it's very different from the type of cracking that I observed in, let's say, the carbonate. So the carbonate sample with up to 10 thermal shock cycles had thermal cracking that essentially widened with up to 10 cycles instead of elongating like with the granodiorite. And not only that, but you can see that the cracking is really, the paths of these thermal cracks is dictated by these vuggy pores that I had mentioned before, which is super interesting. And as I said, I wasn't expecting a lot of cracking in this lithology because calcite doesn't have a very large, very high thermal properties. So I did a little bit more digging and research, and I learned that calcite is actually really unique in terms of its thermal properties. Calcite is what we call thermally anisotropic, meaning that if you heat up a carbonate rock full of lots of calcite, those calcite minerals are going to expand in one direction, but then contract in another direction. And that's going to contribute to the thermal cracking. Also, those vuggy pores in the carbonate serve as stress concentrators. And so this is probably why we see the cracking occurring along those boundaries of those pores. And so we can look at how those different cracking mechanisms affect permeability. We see in the granodiorite that permeability increases by about an order of magnitude. In the carbonate, permeability increased several orders of magnitude, which was really interesting. And we can relate that cracking to the permeability changes through what we call the a cubic law of fracture flow. So basically, this law says that if you want to increase flow through any crack-like or fracture-like features, and you want to change anything about the fracture to do that, basically you want to change the aperture of that fracture. And that's exactly what we're seeing here. We don't see a big change in the aperture in the granodiorite, but we see that crack widening, that aperture change in the carbonate. So carbonates, great. Granodiorite's okay for thermal stimulation. And for the basalt that we tested, well, with up to 10 thermal shock cycles, we saw almost no changes in the thermal cracking, or no changes in the microstructure, which was pretty interesting. And I think that that's partly because we have those lower thermal properties, we have pre-existing cracks, we have equally shaped pores rather than those pinched out pores like in the carbonate. And all of this resulted in not large changes in permeability. And so we're pretty much out of time for my talk. So I'm going to leave this to you to say, if we want to optimize different stimulation methods, it's important to consider the microstructure, and that can help us target different rock types like the carbonate, then the granodiorite, and then maybe the alkali tricky basalt for a method like cyclic thermal shock stimulation. And with that, I'll take any questions you might have.
Thank you, Marguerite. That was great. We do have a couple questions. You might have touched on this, but maybe this will give you a chance to expound on it. What results did you see from the basalt samples?
Oh, yeah, I slipped that in right at the end. Yeah, so we didn't see much change in the cracking. So with up to 10 cycles, I mean, this is the result. So we didn't observe any cracking in the sample. We didn't see any increases in permeability. I should mention the permeability began relatively high compared to the other samples. But yeah, I would not suggest this method for this specific type of basalt.
Great. Another question. Based on the cubic law, flow is inversely proportional to length. As the fracture lengthens with the granite, should that decrease flow with additional thermal cycles? Does this mean that the aperture opening is a more significant effect than the fracture length?
Oh, actually, that's a really interesting question, that as we increase the length, the flow might decrease. It seems like it's not doing a great job at decreasing the permeability here. I mean, there's definitely competing factors, right? So perhaps this increase in permeability here is the culmination of increasing your aperture and your width and the length. And so yes, maybe length could help decrease permeability, but when you consider the increase in width and aperture, basically this is your result. And yeah, the main message is if you're going to change anything in a fracture geometry, it's the aperture that is going to get you the biggest bang for your buck. That's why we are interested in crack widening. That's why proppants are so important to keep fractures open, etc.
Excellent. I think you answered their question. They say thank you. Another question, do you know how long the fractures created continue to open?
Oh, yeah, that's a really good question. And that is something you'd have to consider with a stimulation method like this is we did everything here, or at least we did the stimulation at ambient pressure. So that stimulates basically high pore pressures in the subsurface, right? But we were able to look at permeability under high effective pressures. And so we could see that permeability stayed or remained high in the carbonate at really high effective pressures, as you can see here. So that indicates crack opening. And I do actually have velocity measurements on these samples too that also support the cracks remain open in the carbonate at these higher pressures. So that's some indication of cracks are able to remain open. For the granodiorite, it's not as extensive, right? So the permeability still is open, but I would argue that these carbonate cracks are more stiff at these higher pressures than the granodiorite cracks.
That's wonderful. I think that's all of the questions, but I know, Marguerite, this is just scratching the surface of all of your work. So I'd encourage anyone who has further questions or want to discuss Marguerite's research with her to please reach out directly. So I think there's a lot more there to learn. So great job. Thank you.
Thank you. Thanks so much for having me. It's an honor to be here. So
thank you.
Wonderful. Thank you, Marguerite. That was so well done. And the way you explained it from someone who is not a geologist, like I followed almost all of that. So thank you. I appreciate that presentation. So next up, I'd like to introduce Alex Martin. Alex holds a bachelor's degree in environmental engineering from the University of Colorado Boulder and is currently pursuing a master's in sustainable energy engineering at the Iceland School of Energy. Her thesis focuses on geothermal energy, exploring themes of responsible resource management, cascade utilization, innovation, and the circular economy through the lens of operational processes. In addition to her academic work, she has experience in both high and low temperature geothermal applications in the US and Iceland. Welcome, Alex.
Yeah, thank you for having me. So yeah, my name is Alex Martin. My thesis topic was looking at Hellisheiði power station located in Reykjavik, Iceland.
Alex, I'm so sorry to interrupt you. We're seeing your notes screen. Just wanted to let you know before you got too deep into it. Take it away.
Okay, is this better for you?
Yes, that's perfect.
Okay, amazing. All right. So yeah, I think I'll just start with a little bit of an acknowledgement. And so I'm originally from Colorado. I've spent the last 2 years studying at Reykjavik University, doing sustainable energy engineering. And so I've had the really great opportunity to study, wind, hydro, solar, but also specialize in geothermal energy and study with students from almost every continent, which was amazing. I'd like to take the time to acknowledge my supervisors on the project, Dr. Juliet Newson, she's the director of the Iceland School of Energy, Dr. Atna Paulsdottir, who actually is a previous recipient of the Marcella Lippmann Award, and then Baldur Brynjolfsson, who was my project manager on this. And also some other funding. I was able to pair this work with an internship with Reykjavik Energy, and to do that, I received the Reykjavik Energy Science Fund. And then just to come over to Iceland in the first place, I got the opportunity to participate in the Leifur Eriksson Foundation Fellowship, which promotes the exchange of American and Icelandic graduate students. And so quickly, I'd just like to acknowledge not only what an amazing learning opportunity it's been to go to Iceland and learn about geothermal, but also what an unforgettable experience the last 2 years abroad has become. With like that, I'd like to express my gratitude for the scholarship and discuss my research today. So some of this is confidential to Reykjavik Energy. So even though it's about quantifying, a lot of what I'll talk about today is more of the methods. Thank you. And so this project I've kind of summarized into 3 different parts. And so the first was to develop a geothermal waste profile for a general geothermal power plant. So on a process and equipment level, a lot of my literature and background review focused on identifying sources of geothermal waste, how is this waste being managed, and any relevant regulations or environmental impacts of this waste. I also wanted to look at how this waste can be used, and that's where I brought in concepts like cascade utilization, the circular economy, and something called an eco-industrial park, which is essentially just the use of this waste streams into additional products. And so I looked at examples from all around the world of how geothermal power stations have turned what they would otherwise throw away into additional value. And from there, I moved into a case study for Hephaestus. And so I did this using site visits, interviews, internal data, publicly available data, and then importantly, I got access to their power plant sensors. So I was able to develop a real-time analysis and also any historical trends of any of my flows of interest. And so results from my work, I put on process flow diagrams, kind of showing how every stream interacted with the engineering processes. So where did they go? How are they sent to the existing eco-industrial park there? And then how are they managed and disposed of? And so a really big focus of this part was to focus on total annual waste and distinguish between how much of that is actually available to be contracted out, either for internal use in the engineering processes or existing use in the resource park. And so in part 3, I expanded on those additional flows and I added in some planned projects. Some of these have been announced. So they're going to be adding a geothermal spa to their power station. They're expanding carbon capture and storage technology through companies like Carbfix and Climeworks, and then they also make supplements there. And so after incorporating all of these projects that are planned, confirmed, I recalculated the flows as to what's actually kind of, I guess, available after 2030. And then I explored, what we can do with that. So analyzing any future opportunities, evaluating some of the challenges to that, and then highlighting some of the nuances that would be able to get us there and turn these into feasible projects in the future. And so with that, this is kind of results with all of my numbers taken out, I guess. And so depending on the boundaries conditions of the work, results could vary quite significantly. So it's really important for me to distinguish here that I chose to focus only on annual operational waste. In regards to the production of electricity and hot water, I focused on 2023 and then all historical data since 2020. And so distribution systems and essentially anything that leaves Hephaestus power plant is outside of the scope of this project past it gets made here. And then I also wanted to include scheduled maintenance activities, such as, instances where the turbines get turned off for maintenance, or the heat exchangers in the thermal plant are turned off and cleaned out. These often led to more waste, but they're also essential for smooth operations in a power plant. And so from there, I separated all of these out into products. Here at Hephaestus, it's electricity and hot water. I then went into what I kind of determined to be the main byproducts that get used in internal engineering processes or sent to the resource park. So, examples here: steam, separated water, condensate, gases, especially carbon dioxide and hydrogen sulfide. Those were big ones. And then even smaller products like scale from the heat exchangers or the wellheads, or gland seal water from the gas collection system pumps. So it was quite a large range of waste that I looked at. Also looked at peripheral products. These are things like the chemicals and lubricants. They were not a major focus of this project, and I did quantify them when the data was available, but not all of these could be redirected back to the park, so it wasn't a huge focus. And so for every piece of equipment, And for all of these streams, I mapped out kind of what goes in and what comes out, of the wells, separators, turbines, cooling systems, thermal plant, you name it. And so I also wanted to put where locations of these streams are sent to the existing resource park, housing, importantly here also a hydrogen fuel, like electrolysis. And so really great additional product through On Power, carbon capture technology, silica supplements. And from there, I also mapped out how that's disposed of. So I focused on, the ones that are like very clearly regulated in Iceland. So that's going to be surface discharge, emissions, and deep reinjection, and also injection into the groundwater system there. And then smaller ones like what we ship out to landfills or go through any of our overflows. And so this is a public version of their process flow diagrams. And so I really just want to highlight, each of these colors is a different stream and they go to so many different places. Like if we look at the cold water wells and we just follow the blue stream, it goes into specially fitted condensers. It gets heated. They call it preheated water. The preheated water gets sent to heat exchangers. And through the other side, we send, separated geothermal water. And so really, it's a very simplified version, but a lot of these streams go through a lot of places in the power plant, before ultimately either ending up as hot water, re-injected fluid, or electricity. And so this is kind of where I took it next. All of the work that I did in the results section, it identifies ranges of current available waste. As you know, demand changes over time. And so the exact flow of waste is not going to be the same at the same time of day or even the same period of the year. So I outlined the available range. And then I also mapped out, current cascade use at Hecate. So for example, temperatures at the bottom of the wells are around 250 to 300 degrees Celsius. And in their current systems right now, they utilize that water all the way down to about 60, 65 degrees. For the planned expansions, they added in additional products, like this lagoon that allows us to take that even further, utilizing the 250, 300 degree water all the way down to even 30 degrees. And so it's really great because doing this, it allows for better utilization of your resources. You pay millions of dollars to extract this fluid from wells. You might as well take out as much thermal energy as you possibly can before you put it back in the ground. And it also provides a lot of flexible management, and in some cases can even eliminate any issues or challenges. So for example, one of the planned projects, it's called Carfix Silverstone. It's going to drop Helicety's operational emissions down to net zero by 2026. And then not shown because of some of the confidentiality, I recreated the same map to build on future opportunities and future projects as well. And so to finish off, I kind of started this project with the idea that, I could just make one single mathematical model and it would just predict, how much waste we get for a power plant and show us exactly where we could put it. But quickly, I really learned that the plays between engineering processes, the environment, regulatory bodies, and the economy are quite complex to incorporate into just one model. And so the location of where the waste is used, sent back, or added, it varies and it's important. One waste use option, it may generate multiple additional streams of waste that then require their own management and even contracting flows that don't stay the same, or flows that, like the heat exchanger scale, you just shovel it out a couple of times a year. That can be challenging, but this complexity isn't something to shy away from. And so the resource park at Hecate is arguably quite a successful implementation of the circular economy already. And I'm really excited to see how this quantifying of the available resources we have left can help lead to projects in the future. So thank you. If you have any questions, this is my LinkedIn and my Gmail.
Awesome. Thank you, Alex. That was so great. Such a good example of utilizing the entirety of the resource in the most efficient way possible. I hope that all power plants can do something like that. We have a couple of questions. What sort of considerations did they take into account for the shallow reinjection portion? Do they include injected volume, pre-treating the water, ensuring isolation from aquifers, etc.? Could you expound on that a little bit?
Yeah, so for that, I would kind of say all of the above. They take very careful consideration. So hypotheti, the cold water they use comes from a protected aquifer called Engedaler. And so they have very robust models that they do and they update it every single year. And they do take in injected volume, not so much pretreatment. It just kind of depends what piece of equipment it goes through. If it's going through a heat exchanger, sometimes the water quality doesn't necessarily change. And then, yes, they have certain locations that are mapped out exactly where they can inject to keep that away from the aquifer.
Right.
And then just one more thing on that, for more deep reinjection, where they inject much larger volumes of fluid, something they also monitor that I looked at is like seismic activity. Because if you inject a lot, sometimes you can set off some earthquakes, which has happened in the past. They have now remedied that issue here.
Great. Another question here. How does the waste from geothermal energy power production compare to other forms of energy generation?
Yeah, so I think this one is really specific to what type of waste you're going to look at in terms of emissions. I would say quite low compared to maybe a coal power plant, but in terms of water consumption, I would say really quite high. So the cooling towers at geothermal power stations, they require a lot of makeup water compared to some other forms of power generations. And so in this case, a lot of power plants, instead of using, fresh water to do this, they'll actually use condensate fluid. So like the steam condensate out of their condensers is often just pumped and recirculated back into their cooling towers to help kind of offset exactly how much water they would need to do this.
Great. And then maybe one last question before we move on to Princewill. How, and this is my own question, how applicable do you think either this methodology or kind of your specific findings on recommendations for uses for the waste heat and the processes, like how transferable is that to other power plants, be it in very similar geologies or with different technological applications?
Yeah, I think, of course, one of the biggest things I figured out is like it does really depend on the power plant. Like I learned how like adding acidification and inhibitors could like completely change, the different opportunities you have available to you. But at the same time, a lot of the future opportunities that I could not necessarily share with you, but did discuss, they came from examples from all over the world. And really, if you have the right temperature and the right chemistry, I think you could pull a lot of inspiration. One of the things that I talked about was a cement drying plant, and I looked at one that's currently operating in Kenya right now. And so maybe you couldn't apply it in the same type of engineering way, but I think certainly you could do a feasibility study and learn from each other, if that makes sense.
Absolutely. I think that's great. Thank you so much, Alex. And to everyone listening, we have dropped both Marguerite, Alex, and Princewill's emails in the GChat. So I'm sure they would be happy to keep chatting with you guys about their work. So thank you, Alex. I'll hand it over to Vanessa to introduce Princewill.
Yes, thank you again, Alex. It's so exciting to just hear about all of this and this idea of, we want to have more power plants coming. So let's start off right and maximize the use. And it really ties in the community engagement piece too, when people can enjoy, the workforce and also, the benefits of hot springs. So next up, I'd like to introduce Princewill Okechukwu is a second-year master's student at the University of Padua, specializing in geophysics for natural risks and resources with a focus on geothermal energy. His notable work includes founding the first geothermal energy startup in West Africa and pioneering geothermal research in Nigeria, such as his published study on modeling geothermal energy potential in the Ruwan Zafi hot spring region using aromatic data, which you're going to hear a little bit more about. At the University of Padua, Princewill's research emphasizes innovative approaches to geothermal exploration in areas with limited prior geological data. His work bridges academic rigor with practical applications, aiming to transform energy landscapes through geothermal development. Welcome, Princewill.
Thank you very much, Vanessa. Hello, everyone. Standing on existing protocols already. My name is Princewill Okechukwu, and I am a second-year master's degree student at the University of Padua in Italy. It should not be confused with Purdue. We are in the US, but it's Padua in the US in Italy. So my presentation today will be based on the geothermal energy investigation of the Ruwanzafi hot spring region in Nigeria, of course, using aeromagnetic data. So unlike everyone's presentation today, the previous two individuals, mine is really like from the scratch, not like from a developed country's point of view, but it's one of the first recognizance investigations prior to a successful geothermal energy exploration. So the growing energy demand in Nigeria has come with a lot of environmental challenges, given the notorious experiences we've had with crude oil and the like. So the untapped geothermal potential as a sustainable energy solution, where renewable energy sources account for about 29% of electricity generation globally. So, and the importance, I'm also going to deal with the importance of investigating underexplored regions with potentials. So, of course, we could see here the electricity generation, crude oil, fossil fuels, and renewables down. We could see the thin red line for geothermal, giving a little room for improvement for geothermal. So the area I am after here is the Ruwanzafi hot spring region, located somewhere here in the northeastern part of Nigeria. I'm so sorry I couldn't zoom in. It's closer to the Cameroonian border, which has some highlands that are tectonically active per se. So the geological context of Nigeria is kind of straightforward. It's a combination of basement complexes and sedimentary troughs. And the area, as you can see here, boxed, is located basically in the boundary of a basement complex and the Benue Trough. Literally speaking, the Ruwanzafi hot spring region is located in the sedimentary Benue Trough, and it is the only region where the Bima sandstone outcrops. And the Bima sandstone, geologically speaking, is the only sandstone that is directly overlaying the basement complex in that area. So, of course, the average the spring temperature at the surface is about 56 degrees centigrade at the area. So here we could also see the Lamurde anticline at the middle of this red box here. I don't know if you could see my mouse. And Ruwanzafi is just located at the foot of the anticline, just, how will I put it, perpendicular to the River Benue, which is the second largest river in Nigeria. This is the topographic relief map of the area. You could see the area Lamurde here, as I said, just at the foot of the anticline. And why I'm stressing this is for you to know the causative mechanism beyond causing this geothermal hot spring that is to be investigated. So, of course, the research objective is to investigate subsurface geothermal structures, model the Curie points depth, and estimate the heat flow. and assess the region's geothermal energy potential for sustainable development. And before major wells are being drilled, investments, geothermal power plants are being established, all of these researches are the first thing to be done. So the methodology basically involves aeromagnetic data acquisition and processing. It was gotten from the Nigerian Geological Survey Agency in Nigeria, the equivalent of the American survey too. And the application of spectral analysis for estimation of depth was applied, in which we estimated the depth of the top and the Curie point depth. Also heat flow calculations using the Fourier law. So this is the magnetic anomaly map of the area, as you can see here. So you can find out that there's a lot of magnetic anomaly at this area, and which we're going to discuss further. The technique, of course, it's basically two techniques. I wouldn't want to bore you much, especially for those who are not really geophysically orientated. But it's when you're determining magnetic sources at depth, you either analyze or you do both of them. You analyze the shape of isolated magmatic anomalies, or you consider their statistical characteristics of the magnetic anomaly pattern, of which we basically did the second one. So it's simply by converting the spatial data into the frequency domain, then both techniques demonstrate the relationship between the spectrum and magnetic anomalies. The equations used are basically these, as I said, no need to bore you. So we estimated the top bound and the centroid of the magnetic source by fitting a straight line through a low wave number parts are radially average spectrum. So that is it. So we went further in applying the Fourier law. So in a one-dimensional case where we say the temperature increase, we say that when we assume a vertical direction of the temperature variation, as I said, then Fourier law takes A, then the equation A, the Fourier temperature was defined with B, where ZB is the Curie point depth that we have, and that's etc. So but when we were doing this, because the area, if you saw from the beginning, the area of the map is very large, so we divided the whole area we wanted to study with trying to prioritize the geothermal hot spring region in the middle. We divided it into 5 blocks per se, and in those 5 blocks, we selected it each about 110 by 110 kilometers for per dimension. So we radially averaged the power spectrum block, as you can see over here. And we determined that the depth to the centroid was about 7.2 kilometers with an error of about 0.05 kilometers, which was super accurate. And the depth to the top of the magnetic source to be about 0.89 kilometers, which is even less than a kilometer. So of course, this map here, this graph here, this figure here is the depth to this centroid, which is computed for the first block, of which we average to be about 7 kilometers. So the results are that the depth to the top was about 0.89 to 1.08 kilometers, which shows a very good promise for geothermal energy. How will I put it? Thinking, and you can see that it is sinking, showing you that towards that part, the depth, the top is very, very much low compared to the surrounding area. Moving further, the CPD higher. So you could find that in the middle towards the hot spring itself, we can find that the magmatic causative source of the geothermal hot spring is more closer to the surface here, radially spreading out the heat that has been migrating from the mantle per se. There is not much time to really discuss about the total geologic history, but of course you could read my paper that has been published, and you will find more details on this and about the geological history of the area. So the heat flow was about okay, this is the estimated CPD, it was between 9 kilometers to 14 kilometers deep. Then here we put the depth to the top and the CDD together in kind of a 3D illustration, and you find that while the DTT is sinking, showing a low value, you can see that the CPD is showing a high value, which means it is very much closer to the soil. Meter, and of course, the evidence of magmatic intrusion, which is conductive, which is, positive to geothermal activity. So here we can see the heat flow map again of the area as derived from our calculations, and you can see that it is radially going out from the source in the middle. So then the broader implications of this of my research, which was a research starting about a few years back. My current research at the University of Padova is we're going furthermore, trying to use seismic to map out the fluid migration of geothermal waters from depth. But this particular one is very unique in Nigeria because it shows the relationship between topography and heat flow in the region. Unfortunately, I couldn't get the map of the area, but if we go back, you find out that the Ruanzafi Hot Spring region that is being studied here is located directly on the foot of an anticline. So the earth bulged at that place and probably exposed the sedimentary layer to the mantle per se. So there is a potential for shallow steam production less than 2 kilometers depth, which is very, very much economically viable. And the contribution to Nigeria's energy diversification and climate goals can never be overstated, given that geothermal is base load. My own version is that it has no consequences. So this can be the foundation of future geothermal exploration in the whole of West Africa. So our challenges so far is limited geophysical data coverage in other regions. The Ruanzafi Hot Spring region is the flagship region in Nigeria, which means it's the one with the highest potential. And my startup is currently working on it. It's a long process, but with time, we'll be able to come up with a very viable solution to exploit further. Also, the lack of investment in geothermal in Nigeria is appalling, and need for regulatory support from the oil and gas ministries and the rest, and also to port their expertise and cross over to geothermal is much needed. Collaboration needs, as I said, funding for extended geophysical surveys, partnership with global geothermal experts, etc. So the summary and call to action is that Ruanzafi has significant geothermal potential. Significant, may not be as large as areas in the Rift Valley or in volcanic margins, but this can be able to add a little bit of solace to the precarious energy solution in Nigeria. And research can definitely drive Nigeria's sustainable energy future. of course, we're inviting you all to join the effort to unlock geothermal resources in West Africa. So this is the end. If you have any questions, you could send it to me or follow me on LinkedIn. Thank you very much.
Thank you, Princewill. I think that was great. Super exciting to learn about a little bit about the geology of a part of the world that I don't know very much about. I'm curious what your thoughts are in terms of, I think you were focused on power production for the energy mix in Nigeria, but I'm curious what your research, either this specifically or in general, if there are other opportunities in Nigeria in terms of heating more on like the low and the medium temperature side of things, or do you see the biggest potential in power production for Nigeria?
Well, the biggest potential for geothermal in Nigeria is power production. So sorry if I cut you short there. And it's because, of course, Nigeria is it's about 4 degrees above the equator. So we are generally very hot. So, and we don't really need cooling per se. Probably we don't need heating, sorry, but maybe yes, we need cooling. And if we are talking about cooling, we are going to focus on retrofitting spent oil and gas wells for that. But for giving this particular area the research so far with other ones is showing prospect for electricity use because this year alone in December, and because it is not baseload. And if electricity is the most viable option to go with, and of course, other direct use of geothermal will be for agriculture and the rest in Nigeria. So yes, there is enormous potential for its 220 million people.
Great. We have one more question. Given that there's been so much oil and gas development in the region, is there any lithological or well data available in that region of Nigeria that could help inform further exploration or development in the area?
Of course, Nigeria is the largest oil and gas producer in Africa. Thousands and thousands of wells, both producing and abandoned. So the large and international oil companies are sitting down on legacy well data that they could share, given that the regulatory framework is computed in time. So there has been a lot of efforts to be able to bring them into the mix. Pivot from Inner Space, Jamie Baird, and everyone, including the IG, also interested. So we're working hand in hand. So it's not something that is easy, given that most of these data have of economic value. So, but yes, there are a lot of water-rich wells to be able to produce geothermal energy.
Great. Thank you, Princewill. That was really great to learn about. I think we are coming up at the top of the hour, so I would just like to thank Alex, Marguerite, and Princewill. Thank you so much for joining us and for sharing your amazing research. I hope everyone who has been listening today has enjoyed it, and please reach out to these students and young professionals directly if you have any questions or would like to collaborate with them. And keep an eye out for the next announcement for our next installment of the Full Steam Ahead webcast series. So I hope you guys have a great rest of your day.